If Elon Musk truly had to choose the next battery for the Tesla Model 2, what would he value the most? Would it be cost, performance, or safety? Inside every Tesla, more than 7,000 individual cells work together as one system. If even a single cell overheats, it can trigger a thermal runaway, spreading fire through the entire pack in less than 10 seconds. That's exactly why two next-generation chemistries, aluminum-ion and sodium-ion, are now on Elon Musk's radar. In this video, we'll explore how each of these new battery types deals with heat, overcharging, and long-term wear, and which one could become the realistic choice for Tesla's $13,789 Model 2. Would you trust a cheaper battery if it runs cooler? Or would you rather pay more for something that's proven to be safe for years? Which one would hold up better in a crash or a charging fire? We'll break down all of that right here. You're watching Auto Gear Shift, where we don't chase the hype. We decode Tesla's next moves with real data, smart analysis, and no unnecessary noise. So before we dive in, hit subscribe and ring the bell. Let's push Auto Gear Shift past 15,123 subscribers and keep the flow of tech insights faster than Elon's next post. So, what exactly are these new batteries? When Elon Musk hints that Tesla could move away from lithium, he's referring to two promising alternatives that are close to real production: aluminum-ion and sodium-ion. Both are designed to solve one major problem with lithium batteries: fire risk from overheating. Let's start with aluminum-ion. Instead of lithium, these batteries use aluminum as the anode, a metal that's not only much cheaper, around $2,000 per ton compared to $13,000 per ton for lithium, but also easier to recycle. In 2015, Stanford scientists built an aluminum-ion prototype that could fully charge in just 60 seconds. That's compared to 20 to 40 minutes for Tesla's current fast-charging lithium packs. This huge speed comes from how aluminum stores energy. Each atom can release 3 electrons, while lithium only releases 1, allowing higher current output with less stress on the cell. Safety is where aluminum-ion really shines. Traditional lithium cells use flammable organic solvents that can ignite around 150 to 200 degrees C, while aluminum-ion batteries use an ionic liquid electrolyte, a salt-like fluid that stays stable and non-flammable beyond 200 degrees C. Even if punctured or short-circuited, aluminum-ion cells release harmless vapor instead of catching fire. That makes them appealing for vehicles containing thousands of small cells like the Tesla Model 2, which will likely use around 6,000 to 7,000 per car. Now let's look at sodium-ion, another big contender. Sodium is extremely abundant, making up about 2.6% of Earth's crust, and can be extracted from simple sea salt, meaning lower costs and fewer supply issues than lithium. Its energy density sits around 120 to 160 dke, about half that of Tesla's lithium-ion packs, which are around 250 to 270 dwachek. So yes, sodium-ion powered cars may travel shorter distances per charge, but they stay cooler and are safer under stress. A 2025 study by CATL showed that sodium-ion batteries enter thermal runaway only near 292 degrees C, compared to 346 degrees C for lithium iron phosphate cells and far above the 200 degrees C ignition range for older nickel-based chemistries. Simply put, sodium-ion batteries can handle about 100 degrees C more heat before anything dangerous happens. Even when punctured, overcharged, or exposed to open flame, sodium-ion cells are far less likely to explode because their cathodes and electrolytes don't release oxygen quickly, which is what usually causes EV fires. In short, aluminum-ion and sodium-ion are both being developed to make EVs cooler, cheaper, and safer. Aluminum offers faster charging and extreme heat tolerance, while sodium delivers affordability and wide-scale safety. Together, they represent Elon Musk's next big decision: choosing which one can power the $13,000 Tesla Model 2 without risking safety. When most people think about EV fires, they imagine big explosions and blazing flames. But in truth, it all depends on how a single cell reacts to heat, pressure, or moisture. Both aluminum-ion and sodium-ion are designed to be much safer than lithium, but they each win in different areas. Let's start with heat and explosion risk, the main cause of EV fires. In a 2025 test, large 50Ah sodium-ion cells started reacting around 292 degrees C, roughly the temperature of a car's exhaust pipe. But they didn't instantly ignite. Only around 22% of the cell mass actually burned, and the spread was so slow that it stopped before reaching nearby cells. By comparison, a lithium iron phosphate cell can begin runaway at 346 degrees C and release flammable gas in under 4 seconds, setting off a chain reaction. Aluminum ion cells behave completely differently. Their ionic liquid electrolyte remains stable up to 200 degrees C, and since it contains no organic solvent, it doesn't vaporize or burn even when punctured. In Stanford's later tests, aluminum ion prototypes kept working after 10 minutes at 180 degrees, while lithium ion cells failed in under a minute. However, the aluminum electrolyte does react with water, creating tiny amounts of hydrogen and hydrogen chloride gas, which is why future Tesla modules would need sealed aluminum casings with moisture-resistant coatings. Now let's talk about electrolyte fire risk, which determines how easily a battery pack could catch fire in the real world. Standard lithium-ion batteries use organic solvents like ethylene carbonate, which have flash points around 25 to 30 degrees C, basically the temperature inside a parked car under sunlight. That's why even a minor internal short can cause ignition. Sodium-ion batteries use propylene carbonate, with a flash point above 100 degrees C, over 3 times higher, cutting fire risk by about 70% in lab conditions. Aluminum-ion batteries don't even have a measurable flash point since their molten salt electrolytes are non-volatile. In a 2024 report by the NRE, aluminum-ion cells showed 0 ignition events even when overcharged by 200%. While lithium-ion packs ignited 5 out of 10 times. When it comes to mechanical safety, the differences are also clear. In a 2025 ACS penetration test, aluminum-ion cells pierced by a 5mm steel rod kept over 90% of their voltage and produced no smoke or flame. Standard lithium cells vented hot gas at 400 degrees in less than 2 seconds. Sodium-ion packs didn't perform as cleanly. Tests showed small bursts and ejected material when hit at 50 km/h, but there was no full-pack fire. That's still a huge safety leap compared to lithium, where one broken module can ignite the entire battery in under 10 seconds. Finally, we come to water and humidity risks, especially important during floods or storms. Aluminum ion reacts with water, producing small bubbles of hydrogen and hydrogen chloride gas, but only if it's exposed for hours. Sodium ion performs slightly better. Submerged cells showed almost no reaction for 6 hours, then slow gas buildup afterward. Both depend heavily on Tesla's battery management system and waterproof housing. Similar to the company's current 4680 packs that meet IP68 standards, offering full protection from dust and water for up to 30 minutes at 1.5 meters deep. So, what's actually realistic for Tesla? When we talk about Tesla's next move, one fact is clear. Safety means nothing if it can't be mass-produced. That's where sodium-ion currently leads. Unlike aluminum-ion, which still mostly exists in labs, sodium-ion batteries are already hitting the market. Companies like CATL, BYD, and Ferrosis have pilot production lines with real cells now being installed in small EVs and energy storage units across China and Europe. Their manufacturing costs are already about 30% lower than lithium-ion because sodium is so cheap, around $300 per ton compared to $13,000 for lithium. This affordability, paired with existing supply chains, makes sodium-ion a practical option for the base Model 2, especially if Tesla wants to meet its $13,500 target without sacrificing quality. There's solid safety data too. Dozens of independent tests from UL Solutions, CATL's 2025 results, and China's EV fire safety regulators confirm that sodium-ion packs can pass crash, nail penetration, and overcharge tests with 0 ignition events. That maturity gives Tesla something vital, a proven chemistry ready for mass rollout now. Sodium-ion may not be revolutionary, but it's ready for real-world use. Aluminum-ion, on the other hand, is the wild card, the kind of bold experiment Musk enjoys. It promises what lithium can't: near-zero fire risk, ultra-fast charging, and easy recyclability. But for now, it's still in prototype stages, far from commercial scale. The main issues are electrode corrosion and sensitivity to moisture. both of which limit lifespan and make large-scale production risky. Experts believe it'll take at least 3 to 5 more years before aluminum-ion becomes stable enough for mass manufacturing. If it succeeds, it could become the first truly zero-fire risk EV battery, changing how Tesla designs cars, maybe even removing the need for fireproof barriers or complex cooling systems. For now, though, Tesla has to balance vision with practicality. Sodium-ion is the logical choice for 2026 to 2027, while aluminum-ion remains a long-term dream for the 2030s. If Elon Musk sticks to his usual pattern, release practical tech first, then improve it through software and hardware updates, the Model 2 will almost certainly launch with sodium-ion. And when aluminum-ion is finally ready, it might power the next generation of Teslas that never burn no matter what. So, after all that, the big question remains, what battery would you trust in your Tesla Model 2? Sodium-ion, affordable, tested, and mass-ready? Or aluminum-ion, futuristic, ultra-safe, but still experimental? Whatever Tesla's final decision is, it could reshape the entire EV industry for yay.